Okay, in this section we're going to be revisiting the idea of a standard matrix of a linear transformation, which we're now going to call a matrix representation. Okay, so when we talked about a standard matrix before, it was specifically talking about a standard matrix of something that goes from R to the N into R to the M. And we would always take T of 1, 0, 0, T of 0, 1, 0, T of 0, 0, 1, and those would be the columns of our standard matrix. We're going to do almost the same thing, or exactly the same thing, for what's called a matrix representation. The only thing that's going to be different is we're not going from R to the N into R to the M. We're going to be going from random vector space into random vector space. In order to be able to pull this off, we're going to need to find an ordered basis for each one of those. So my example I have written down, suppose we know two ordered bases ahead of time of our two vector spaces, and define a linear transformation by blah. We know what T does to each of the three starting basis vectors. Okay, if I want to find the matrix representation, which is playing the same role as a standard matrix, relative to those two bases, I need to find T of each starting basis vector, but I need to write them in terms of my ending basis. So if you look at W1 plus W2 as an output, it doesn't make sense to write that in terms of this basis. I would have to write it in terms of the basis that it lives in. It lives inside capital W. We need a basis of capital W. So T of V1 is W1 plus W2. What I would like to find is what is its coordinate matrix or coordinate vector relative to B2. And from the previous video or the previous section, we have to figure out how do we write it as a linear combination of vectors from B2. Well, it's already explicitly a linear combination of vectors from B2. The coefficients are both 1s, and so your coordinate matrix or coordinate vector is going to be 1, 1. And I can do the same thing for T of V2. Each starting vector relative to the ending vector, or distracted by cat. Okay, anyway, we want each starting vector, take T of it, and then write our answer as a coordinate vector relative to the ending vector space. Okay, in this one case, our coefficients are 2 and negative 1. And then the last one, T of V3. The coefficients are going to be 3 and 4. Okay, so the matrix representation of T relative to these two bases is going to be the matrix with these three as columns. And again, it's important that we have ordered bases so that we know what order to put the columns in. V1, V2, V3, so we put them in the order that I have them. 1, 1, 2, negative 1, 3, 4. Okay, one other cool consequence of this. Suppose I give you a vector and I want to find T of that vector. We actually have two convenient ways to do it. Option number 1, if you take T of this particular vector, it's a linear combination of things from our basis of the domain. One way to take T of V is to say it's T of V1 minus V2 plus 2V3, and then use the fact that T is linear. So split this up into T of V1 minus T of V2 plus 2 T of V3. And then we know what each of these are. These were defined in the original problem. T of V1 was W1 plus W2. T of V2 was 2W1 minus W2. And T of V3 was 3W1 plus 4W2. So using the fact that T is linear, we can split it up into T of things that we already know, and then we just plug them in and then combine like terms. Let's see. If we combine the W1s, we have 1 minus 2 plus 6. 1 minus 2 plus 6 would be 5. Our W2s would be 1 minus 1 would be plus 1. 1 plus 1 plus 2 times 4, 8. So 1 plus 1 plus 8 would be 10 W2. So that's one way to find T of V. A second way that we could find T of V is by using matrices. T of V relative to our ending basis is actually just going to be A times our vector V. And I guess we'll have to write V as a matrix, so I guess we'll have to write V in terms of the matrix or the basis it makes sense to use. So let's write a matrix for V relative to B1. Let's see, so our basis was V1, V2, V3, so the coefficients of V relative to B1 would be 1, -1, 2. So this is how we write V as a matrix, or as a coordinate matrix, coordinate vector. We already found the matrix A was 1, 2, 3, 1, -1, 4. And so if we multiply these, first row times first column would be 1 minus 2 plus 6, which looks like 5. And our bottom entry is going to be 1 plus 1 plus 8. 1 plus 1 plus 8 is 10, which means that T of V is 5 times the first vector plus 10 times the second vector. So we get the same answer either way, using a matrix or using the fact that T is linear.